6.3 logarithmic functions. Let's first review the definition of logarithmic functions. What is logarithmic function? I will write a short kind of definition for logarithmic functions, correct? If b is greater than 0 and b cannot be 1, the exponential function f of x equal b to the power of x, this function is increasing or decreasing. This was the definition of exponential function, which I reviewed with you in 6.2. If b is greater than 0 and b is not 1, it's greater than 1 or between 0 and 1, this function is increasing or decreasing. And at the same time, and this function is called, or let's say this, and this function is a one-to-one function. We saw this the other day. F of x equal b to the power of x, you are dealing with this graph, increasing or decreasing like this. And you know both of them, we can call them a one-to-one function, because if you do the horizontal line test on these two graphs, your horizontal line intersects the graph only once. Your horizontal line intersects the graph only once. That's why it's a one-to-one function. Okay, at the beginning, in the first day of your Calculus 2 class, I told you that any function that's one-to-one, it has an inverse. Then f of x equals b to the power of x, definitely this function has an inverse. We call the inverse of f of x equal b to the power of x logarithmic function. Or in a very simple language, logarithmic functions are the inverse functions of exponential, correct? The notation for logarithmic function, log or log, is b, log base b, log base b. That's the notation for a logarithm. Now, if you see in a graph, if I want to show you in a graph, the relation you can see, because I told you that logarithmic functions, they are inverse of exponential functions. For example, if I draw this function, exponential function, passing from 1, and here is 1, and if I draw this line for you, y equal x, if I reflect the graph of y equal b to the power of x, or f of x equal b to the power of x, which is this black graph, if I reflect this one, this graph comes here. The red graph, f of x, is equal log of x base b, or y equal log of x base b. In this graph, clearly you can see that a logarithmic function is the inverse of exponential function. Now, when you graph this, when you see this graph, it's really easy for you to talk about the domain and range of logarithmic functions, correct? The red graph is the graph of log. The domain of logarithmic function, as you see here in this graph, it starts from 0 and goes to infinity. Then your domain starts from 0 to infinity. Range for logarithmic functions starts from negative infinity. You see this part of the graph is going down and this part of the graph is going up, up, up. It's kind of growing, this graph, but with logarithm, the growth is really slow. It's going up, but it's going up really slow. That's why some students, they're asking, okay, where it's turning, it never goes to infinity. No, it goes to infinity, but very slowly. Then you can say the range of logarithmic function starts from negative infinity to positive infinity. And if you think about, or think it this way, the other day I gave you the domain and range of exponential function. The domain for the exponential function was from negative infinity to positive infinity. And the range for exponential function was from 0 to infinity. Now, because we know that f of y equals x, right? Then definitely f inverse x is equal y. This is our definition for the inverse functions. What does it mean? It means the domain of a function becomes the range of the other function. The range of your function becomes the domain of the other function. And you can see in this graph, the domain of y equal b to the power of x becomes the range of log x base b. The range of f of x equal b to the power of x becomes the domain of log x base b. That was a kind of review to talk about the domain and range of logarithmic functions. Now, before jumping to calculus of logarithmic functions, let's review the properties of logarithms, which is again a review for you from college algebra, pre-calculus, even intermediate algebra, right? Intermediate algebra, college algebra, and pre-calculus. Properties of logarithms. In your calculus book, they're focusing on 3 main properties of logarithms. They want to just review those 3. But here, I will give you the list of all 8 properties of logarithms to help you to kind of remember back what was the rule of logarithms, correct? Property number 1. If you have log of x times y base b, it means if you have the log of a product, when you expand the log of product, you can write as an addition of 2 separate logs. You can write log of x base b plus log of base by. Property number 2. If you have log of base bx over y, quotient rule, in this case, Expanded form will be log of x base b minus log of y base b. Property number 3, exponent rule. If you have log of x to the power of r base b in expanded form, you can write as a r log of x base b. This 3 rules is also in your book at the beginning of 6.3. I will add few more, maybe you don't remember them anymore. Rule number 4, right? Because sometimes you need to use these also. Rule number 4. Log of 1 base b always gives you 0. The reason why log of 1 base b is 0, because a to the power of 0 is equal 1, right? An exponent. Number 5. Log of b base b is always equal 1. Number 6. Log of b to the power of x base b is always x. Number 7. Log of, or let's say for number 7 this way. B to the power of log x base b again gives you x. Property number 8. If I have log of x base b equal log of y base b, from here immediately you can say x equal y. We call the property number 8 as one-to-one property. One-to-one property. Correct? This was a review again, all rules of logarithms, and based on these rules, let's do a few easy examples, then slowly move towards the calculus of logarithmic functions. Correct? Let's do a few examples. Example number 1. Evaluate. Log of 81 base 3. If you look to your calculator, if you want to use your calculator to find the logarithm of 81 base 3, your calculator will show error for you, because your calculator is only programmed to calculate the logarithm of the numbers or the natural numbers base 10, not any other base. If your base is not 10, then your calculator cannot calculate that. How to find now the logarithm of 81 base 3? If you remember, you're trying to change 81 as a 3 to the power of a number, correct? I will write log of base 3. 81 is actually 3 times 3 times 3 times 3. If I multiply 4 times to itself, it gives me 81. Then instead of 81, I will write 3 to the power of 4. Now, based on the rules of the logarithms, you can bring always the exponent to the front, correct? Then you can write 4 log of 3 base 3, which is equal 4 times log of a number with the same base. Log b base b is always 1. Here, log 3 base 3 gives you 1, and 4 times 1 gives you 4. That's a quick review. I'm sure in this level that you are in Calculus 2 class, you know all these problems very well. You have no problem to dealing with such a easy problem of logarithms, correct? Let's do another one, example. Again, evaluate. Log of 0.001 base 10. I'm writing base 10, but most of you, everyone knows that if there is no base here, it means that logarithm is base 10, correct? Now, how to change 0.001 to find base 10? You may use here your calculator, but the easy way, even you don't need a calculator. Instead of log of 0.001, can I write log of 10 to the power of -3? Changing this number to scientific notation, from decimal form to scientific notation as a power of 10, and your base is 10. Now, bring the exponent to the front. You can write this one as a -3 log of 10 base 10. Log of 10 base 10 again becomes 1. It becomes -3 times 1, which is equal -3. Correct? A quick review. Let's do one more example. Different one. Expand. A logarithm is given to you in condensed form or as a one logarithm. Log of a square root of x minus 1 over x plus 1 base 10. In this problem, they are asking you to expand. If you look to your quotient rule, which was log of x over y base b equals log of x base b minus log of y base b. I will apply this rule. The right side is the expanded form. The left side is one single logarithm. First thing to do, change the square root in the notation form as an exponential form, right? You can write log of x minus 1 over x plus 1 all to the power of 1/2 and the base is 10. Now, can I write this one as a log of x plus 1 to the power of 1/2 over, x minus 1. The top we have minus 1, not plus 1. Log x minus 1 to the power of 1/2 over x plus 1 to the power of 1/2 based on the rules of exponents. Now I will apply the quotient rule. I can write this one equals log of x minus 1 to the power of 1/2 minus log of denominator. Log of x plus 1 to the power of 1/2. Both of them is base 10. We are not done yet. They are asking us to expand. Here I see the power. Here I see the power. Bring the exponent to the front of the log. You can write this one as a 1/2 log of x minus 1 base 10 minus 1/2 log of x plus 1 base 10 final answer. You change from single form as a one single logarithm to expanded form, correct? One more example. Just a quick review of logarithms. Write as a single logarithm. Log 4 base 10 plus log a base 10 minus 1/3 log of a plus 1 base 10. A problem is given to you in expanded form. They're asking you in this problem to write this expanded form as a one single logarithm. This problem is the opposite of the previous example. Your last step, which was bringing the exponent to the front of the log, becomes the first step in this problem. If you have a number in front of the log, you have to move this number back to exponent. It means here I will write log 4 base 10 plus log a base 10 minus I'll move this 1/3 back as an exponent minus log of a plus 1 base 10 to the power of 1/3. Now here I have addition between two log. Addition becomes a product. Then I will write as a one single logarithm between these two terms, log of 4 times a base 10. Base 10 minus log of a plus 1 to the power of 1/3 base 10. Now I have subtraction. If I want to write as a one single logarithm, it becomes quotient. Log of 4a over a plus 1 to the power of 1/3 base 10. One more step, you can change this power as a, in the radical notation, you can write log of 4a over cube root of a plus 1 base 10. You change the expanded form as a one single logarithm, correct? Up to here, it was all review of the logarithm properties or rules, correct? Now let's start slowly the calculus of logarithmic functions. First, limit of logarithmic functions. Again, if b is greater than 0, then you can say the limit of log x base b as x approaching to infinity gives you always infinity. How? Why? Let's see the reason. Even I graph the logarithmic functions for you, right? If this is the graph of a logarithmic function like this, if this is the graph of log x base b, here is 1, here 0, as x approaching to infinity, as you are moving to the right towards positive infinity, here you can see log of x base b is moving up towards what? Towards positive infinity. When your x is moving towards infinity to the right, your log is moving up towards positive infinity, correct? That's the reason, that's why. The limit of log x base b as x approaching to infinity equals infinity. You have to memorize this. Number 2, limit of log x base b as x approaching to 0 from right. always gives you negative infinity. Let's explain why. Again, I can show you in the previous graph, but let's do another graph. I easily can show it for you. Here y, for example, here y. This is a graph of logarithmic function. Here is your 0. As x approaching towards 0 from right, correct? Here is your 0. You can move only, you can approach to 0 from right side, not from the left hand, because y equals 0 is a vertical asymptote. The graph of logarithmic functions cannot cross the line x equals 0 because the y-axis is a vertical asymptote. Now, as x approaching to the right towards 0, you see your graphing is going down. The log graph is going down towards infinity. That's why we have the limit of log x base b. As x approaching to 0 from right, it's equal to negative infinity. These are the two rules of the limit of logarithmic functions. Let's do now an example, correct? Find the limit of log tan square x as base 10 as x approaching to 0. Let's name tan square x, for example, t. As x approaching to 0, if I plug in here 0, tan square of 0 is always 0, right? The tangent of 0 is 0. Now, if I substitute here t instead of tan square, I will change as x approaching to 0. You see the limit of log of t base 10 as x approaching to 0, tan square of 0 is 0. Then here I will say as t approaching to 0, as x approaching to 0 from the right, then I have a notation for this. The limit of log x base b as x approaching from the right from 0, that always goes to where? To negative infinity. Correct? Later you will use this one in a bigger problem. These two rules. Actually, this example was the only example in your book, and it's really easy. You just have to memorize the two rules of the limits for the logarithms. Right? Now, natural log. Or natural logarithms. If you have log x base e, and now you know e, which number is e? Instead of this notation that you write log x base e, we write ln x. And we call ln the natural logarithm or natural log. Correct? The reason is here. If you have e to the power of y equal x, correct? Easily from here you can say ln x equals y, correct? Exponential form, logarithmic form. If I have e to the y equal x, then ln x equals what? Y. We call these functions natural log. The rules or the properties, correct? The properties of natural log is the same as the properties of logarithms base 10, correct? The only three of them that it's a little bit different because E is involved. I'll write only those three for you. The rest is the same as 8 properties of logarithms, correct? Let's do those. Number one, if you have ln of e to the power of x, believe me, we use a lot this natural log in calculus. You will see it a lot to the end of the semester, especially this part. Ln of e to the power of x is always x. Remember this. Why? Why it's x? I'll explain to you that in rule number 2. Ln of e is always 1. Every time that you see, let me tell you this way, ln close to e, ln e, or e to the power of ln, this part, the answer is 1. Correct? Number 3, if you have e to the power of ln x, I told you, when you see e and ln close to each other, this part becomes 1, then your answer is what? X. This 3 you have to memorize. The rest, number 4, 5, 6, the product rule, the quotient rule, the power rule, all of them is the same as logarithms, correct? Let's do one quick example or two, maybe. Example number 1. Solve. E to the power of 5 minus 3x equals 10. This is an exponential equation. To solve this exponential equation, the only way to solve it for x, because your x is in the exponent, you have to bring it down. How to bring it down from exponent to the base? Apply ln or take the ln from both sides. You can write ln e to the power of 5 minus 3x equals ln 10. Correct? Now, based on the rules of the logarithms, the exponent can come to the front of ln, right? Or ln e, I told you ln e is always becomes 1, correct? Which way you go, both of them is the same. Ln e is 1. Or you can bring the exponent first here, 5 minus 3x, ln e equals ln 10. Now, ln e becomes 1, then you can write 5 minus 3x equals ln 10. Now it's an easy equation. You can solve it for x. First, subtract 5 from both sides. Then negative 3x equals ln 10 minus 5. If you multiply both sides by a negative, or if you multiply both sides by negative 1/3 in one step, let me show you in 2 steps. Maybe some of you ask why it's going like this, correct? First, I will multiply everything by negative 1. Then 3x equals 5 minus ln 10. Now, multiply both sides by 1/3. Then x equals 1/3 of 5 minus ln 10. Final answer. If you use your calculator and find how much is ln 10, then subtract it from 5, then multiply it with 1/3, you can find an approximation answer also. The exact answer is 1/3 of this, because ln 10 will be a decimal number with a long decimal place. Because you're rounding off, then if you want to do that, your answer will be approximate, not an exact answer. But this format gives you an exact answer, right? Example number 2. expressed as a single logarithm. Expressed as a single logarithm or single log. The problem is ln A plus 1/2 of ln B. Again, rules of logarithms. Right, as a one single logarithm, if you see a number in front of ln or log, you have to move it to exponent first. Then you can write ln A plus ln B to the power of 1/2. Now, we change addition to product. Then you can write ln of A times B to the power of 1/2. B to the power of 1/2 means a square root. You can write your answer as a ln of A square root of B final answer. You see, it was an expanded form. You change it as a one single logarithm. Now, limit of ln. Number one, limit of ln x as x approaching to infinity gives you always infinity. The reason again is the graph of the ln, right? If this one is the graph of ln, as x approaching towards infinity, your ln is approaching also toward the infinity, the ln graph. Ln x is also approaching infinity. Number two, limit of ln x as x approaching to 0 from right always goes to negative infinity. You see, as your x approaching to 0 from the right, the graph goes down to negative infinity. That's why these two rules exist, or these two limits are exist, correct? You have to memorize these two limits also. The last thing that I want to discuss in this lecture is change of base formula. Sometimes you are dealing with the log of a number that even your calculator cannot calculate for you. For example, if I ask you what is log of 5 base 8, if you enter, if you search this log in your calculator cannot give you an answer. How to find an approximation for such a logarithm? We have a formula for that. If you are looking always for the log of x base b, then it's equal to the ln x over ln b. That is, this formula, we call it the change of base formula. Now here, log of 5 base 8, I can write as a ln of 5 over ln of 8. And if you look to your calculator now, how much is ln 5 and how much is ln 8? If you divide those, you will end up with approximately 0.7739. Correct? But in this format, if you enter log 5 base 8, your calculator cannot calculate. But if you go this way, ln 5 over ln 8, you will end up with this number. We call this formula the change of base, which was again a review from your college algebra or pre-calculus class. This was all about 6.3. 6.3 is not focusing on the derivatives or derivatives of logarithmic functions or ln functions. In 6.4, we will discuss those plus integrals. 6.3 was just a review of logarithmic rules, properties, and also a little bit about the limits of logarithmic functions. I will stop the lecture right now. And you will see my next lecture in your Canvas 6.4, which is about derivatives of logarithmic functions.